Assalamu alaikum everyone. Boundary value problem. In the previous video we did initial value problems, that how we are converting the initial value problem into Volterra integral equation. Now we are going to convert boundary value problem into Fredholm integral equation. So first example is you have to reduce the following boundary value problem into an integral equation. This example has basically three parts. First of all, you have to convert the given boundary value problem into integral equation. And then after converting, you have to express that integral equation into this form, where kernel is equals to this one. And then after doing part B, whatever integral equation you are getting at the end, you have to derive it conversely back to the given differential equation. So basically in this one question, we are doing so many parts. So the first thing, we have to convert this differential equation into integral equation. So first of all, just move the lambda y on the right side and then integrate both sides with respect to x from 0 to x. Second derivative will be converted into the first derivative, plug in the upper limit minus lower limit, and minus lambda integration from 0 to x y of x dx. We know that y prime of 0 will be some constant. We don't have its value right now in this question. So we can just write it as any constant c. Move the c on the right side. After moving it on the right side, again we are going to integrate that equation. This first derivative is going to convert into just simple y, and then plug in the upper limit x and the lower limit 0. Integration of c is going to be cx. So it's cx. It will be like c x minus 0, like upper limit minus lower limit, and then minus lambda integration from 0 to x y of x dx square, because there is coming another integral here, so you write here dx square. Then you know that this is the second integral. Y of 0, the value is given in the question, and that is 0. Dx square means double integral, so we can convert this multiple integral into single integral by writing x minus t. Two integrals were involved, so write 2 minus 1 divided by 2 minus 1 factorial like this and simplify. Now we are going to plug in, you know that we have another condition here, y of L equals to 0. So just plug in that equation x as L. So in place of x, we are going to plug in the L like this. Y of L is given in the question, and that is 0. CL minus lambda 0 to L minus ty of dt. We can get the value of CL here. Keep it here, move this on the left side. So CL equals to lambda, this integral, and C will be equals to lambda over L, integration from 0 to L minus ty of t dt. So we got the value of C. So put the value of C in equation number 2. This is our equation number 2. Just plug in the value of C here. When we'll plug in the value of C here, we can see that we have two integrals. This is not Fredholm integral equation, because you can see these two are the constant limits, but this is 0 and the upper limit is variable here. So we can just simplify it by splitting this limit. You know, this is from 0 to L. We can write it from 0 to x and then x to L. We are introducing another variable here. 0 to L, we can write it here 0 is less or equals to x is less or equals to L. So one integral from 0 to x with the same terms, and other integral from x to L with the same terms. Now you can see that you have two same integrals with same integral limits. We can combine them, write the integral one time, and just combine these terms, integrands, together, and write x integration from x to L as it is. Now what we can do, just simplify here. After simplification, we'll get this equation, and then finally our equation will be reduced like this. Now if you look at this, we can see that we have lambda same, we have y of t same, but we have here this thing different. There are two different kernels here, so we can write the kernel of xt into piecewise function. So first one is when your t is from 0 to x, so 0 is less than t is less than x, and second kernel of xt is from x to L. So we can write it combined from 0 to L, 0 to L, k of xt y of t, where kernel is defined like this. So your B part is also solved up here, that how you can convert this part A into this form. Now in part C, you have to verify directly that the expression obtained satisfy the piecewise differential equation at end conditions. So what we are going to do, we have to consider the integral equation, final integral equation. Now you have to put your conditions. X is equals to 0, you got this first condition. Put x is equals to L, you got the second condition. Now differentiate this equation 1 using the Leibniz rule. So we are going to differentiate it using the Leibniz rule. This Leibniz rule is explained to you again and again. So it is written here. You can follow these steps and we'll get finally this one. Again we are going to differentiate it. So we'll get here y double prime, and again you have to apply the Leibniz rule here. After differentiating and simplifying, we'll get this equation that was the same as our given question in the start. You can see it's the same. So in this way we can prove it conversely. After that you can try this assignment question as well. You can note down this question and you can try this. But keep it in your mind, your kernel of xt is written according to the limits for x and your integral is for t. So don't do it directly. Just think about it. Your integration is with respect to t and your limits of integral are with respect to x. So first convert these into t. How we can convert this middle one into t? We just have to replace x with t and t with x. After replacing x with t and t with x, we'll get here 0 is less or equals to t is less or equals to x, and here we'll get x is less or equals to t less or equals to 1. And here what we will get? We'll get here 1 minus x t, and here we'll get 1 minus t x. And then you can solve it. After this one, we have this exercise 4. You can try doing this exercise. You can note down these questions. You can try these methods of chapter number 2 on this exercise 4. Be careful about the limits of integration and about the limits given here in the kernel. There are many questions here in this exercise. You can try all of these. So I hope everything is clear to you for this chapter, and then we are going to just start the chapter number 3.